Okay, so let's get started. So today we are going to continue our discussions on the RRAM. And first we are going to discuss some array-level integration issues and show some prototype chip. So first of all, here is a map of the major players in the business of the RRAM research and development. And it's a worldwide kind of activities here. And many companies are involved in the R&D and many universities. So in the US, and like Intel and the SanDisk, now like Western Digital, they have the activities. And of course, HP Lab proposed the concept of the memory star. And they are still working on this. And in terms of the universities, so here's a list. So there's no Georgia Tech because I didn't add myself there. So Arizona State because of me. Okay. So this is the major players, and let's look at some of the chips reported in the major conferences like ICC in the past 10 years. So this is the one from E-Tree. As we discussed, E-Tree is a research lab in Taiwan. And this one is based on the hafnium oxide. And the device parameters are shown here. And at the circuit level, so it is integrated into a 4 megabit 1T1R array in the like 0.18 micrometer or 180 nanometer CMOS. And then it has demonstrated MLC, multi-level cell operation. Of course, you can use it as 1 bit per cell, which you can write and read faster, like 8 nanoseconds. Or if you use 2 bit per cell, then the write speed decreases to 160 nanoseconds. This is because they have to do this write and verify. Because initially, if you do this kind of 4-level operation, so this is the resistance, and you have distribution of the resistance. And there are overlap between the tail bits, between two adjacent levels. So you need to open the gap between the adjacent level. So you need to do this write and verify, similar as the NAND flash. So you have to program it and read it and compare to your target. If it does not meet with your target, then you have to reprogram it. So by doing this verify, then you can make the gap between the levels, and then here you can achieve like 4 levels, 2 bit per cell, but you have to sacrifice the speed down to 160 nanosecond. So in this design, the cell size is about like 9.5 f squared. And then this is another example from Panasonic, and the material system is based on the tantalum oxide. And here it demonstrates 8 megabits. This is cross-point array, and with the diode or selector based on this kind of silicon nitride. So it's a exponential IV kind of selector as shown here, and then it's integrated with RRAM, so it's like one selector, one RRAM in the contact via. So this is the cross-sectional view of that contact via. So in this chip, it is integrated still at the 0.18 micrometer technology, and the capacity is 8 megabits. And the chip level performance here is like 400 megabytes per second write throughput. So it enables 64-bit parallel write, and each write event is about 17 nanoseconds. So this is the chip from the Panasonic. This is cross-point array. And then there's another example from the collaboration between National Tsinghua University and the TSMC. So this is done at TSMC 65 nanometer and 4 megabits. And here are the parameters of this design. I will not read the details. And then the SanDisk and Toshiba jointly developed this metal oxide RRAM chip, and the material is undisclosed, so I don't know what oxide. So I just put a ME metal there. But this is a cross-point array, and actually this is very similar as the 3DX point. If you look at the stack, it's 2-layer cross-point, and with the middle layer is a shared bit line, and then there are 2 word lengths, the top tier and the bottom tier, and then this is one S1R because you have the the resistor and the selector here. And if you look at this is a cross-sectional view of the chip, and this is very similar as the 3DX point. So in the 3DX point, we have this kind of cross-point array in the top level interconnect, and then the peripheral transistors is at the bottom. So this chip has a very large capacity, 32 gigabits, and because the pitch is pretty small, and the feature size is like 24 nanometer. So the wire width for this bit line over line is like 24 nanometer. So the pitch is about 48 nanometer. So this is the SanDisk and Toshiba's chip, and then this is but in this chip I think the speed is kind of slower, so the read and write latency is on the microsecond level. So we will discuss more details about this chip later when we talk about the array level design, the peripheral circuits, and we will discuss why this is slow like this. And then Sony and Micron jointly developed this CB-RAM chip. CB-RAM is conductive bridge random access memory. So this is based on the copper diffusion into the oxide to form this metallic bridge. And this chip is 1T1R, and the capacity is 16 gigabits, and the technology node is 27 nanometer, and the cell area is close to 6F squared because they use the DRAM kind of design rule. And the read bandwidth, like 1 gigabyte per second, write bandwidth 200 megabyte per second. So those numbers are pretty good, much better than the NAND flash. Okay, so those are the demonstrations from the industry in the past 10 years. And the recent chips achieve like gigabit density, like 16 gigabit or 32 gigabit. So this is similar as the, let's say, the 3DX point kind of density. And if you look at the initial design of the SanDisk and Toshiba, they are very like the 3DX point design. But they didn't make it eventually, because I think those still the yield and the reliability are the concerns for those prototypes. Okay, so let's talk about the applications. And we have discussed that the storage class memory. So if we keep making the like a gigabit level chip, like the SanDisk or the Micron chips, then it may be suitable for the storage class memory, similarly as the 3DX point. But beyond the standalone memory, we discussed that those embedded memory applications may be another market for the RRAM, because it is compatible with the logic process, especially at those older technology nodes. So here, for example, Panasonic, we have seen the prototype from the Panasonic in the previous ISCC paper. But actually Panasonic made a product out of the RRAM even back in 2013. So you can buy it. I think this is from some website, and you can order it. And Panasonic is the first one to commercialize the RRAM into some product. So this is mostly used in the microcontroller as the embedded non-volatile memory. So the capacity is at the megabit level. So the there's a competition in this market, embedded non-volatile memory. So the target is to replace the eFlash and embedded flash, basically low flash. And here are some comparison at a 65 nanometer node. So if you use RRAM versus the flash, eFlash, so then you can reduce the macro size, the chip size, and also you can reduce the power for the write operation. And then the other characteristics are similar, like the read time, write time, and so on. So then that's a key motivation to use the RRAM for the embedded memory. Of course, this is 65 nanometer, so you can still use eFlash. But the challenge for eFlash is that it's very hard to scale below 40 nanometer, so the cost is so high. So the possible application is that if we can have embedded RRAM at 28 nanometer or beyond that, so then there will be something that the RRAM will not have competitors, because eFlash is not there. So this is the embedded application. And in terms of the embedded application, recently Intel and TSMC both announced their embedded platform for the RRAM. So if you look at this year's ISCC, Intel has a 22 nanometer RRAM process in their FinFET platform. And TSMC last year ICC has a 40 nanometer RRAM. So those are for embedded applications. The capacity is megabit level. So the target is to replace the eFlash.
Is the 1T, 1R?
Both are 1T, 1R, yeah.
The T is FinFET.
For Intel, yes, T is FinFET.
So because there's still a filament formation, so there is a temperature increase locally.
Mm-hmm.
I'm wondering if embedded flash is a bad idea just because you have a processor and like if that thermal dissipation is a challenge or not.
You mean for RRAM or for Flash?
For RRAM.
For RRAM?
Yeah, like because they're using it in embedded as a replacement for embedded flash. Right?
Yes, yes. So you care about the retention, data retention, right? So you need to evaluate the temperature of your chip, and then but generally, as we discussed, the guideline for non-volatile memory is that you need to maintain the data for 10 years at 85 degrees C, right? So if your product, the RRAM, can satisfy that requirement, then it should be okay.
And also, is there a reason like mainstream companies are preferring OXRAM over CBRAM?
I think it's mostly due to the material, let's say the contamination issues, because the CBRAM typically use copper or silver as the active electrode. So those are very fast diffusive into the, let's say, important transistors. So you need to have some barrier to prevent that. So it's, especially silver is not used at all in the silicon process. It's very dangerous. So that's why I think they prefer the oxide, because those oxide materials are very compatible with today's CMOS fabrication. They use hafnium oxide, so it's the same as a high-K dielectric. Okay, so this is the status of the embedded non-volatile memory. And so if we really want to push the RRAM into the standalone memory business, or let's say to do the storage class memory, so we still need to increase the density or capacity of the chip to the gigabit level, or tens of gigabit or hundreds gigabit level. So to do that, of course, we can do this similarly like 3D point. We can do this simply stacking layer by layer. But another possibility is that we can do this so-called bit cost effective 3D integration. So basically the same as the vertical channel NAND flash. So the first one is this horizontal RRAM. This is basically the same as layer by layer simply stacking. So you have the cross-corner array stacked over each other layer by layer. So you have to use lithography to develop to define the features in each layer. So the number of litho step or number of the mask increases as the number of layer or number of stack. So this is not very cost effective. So what we can do is to use this vertical channel, similarly as a vertical NAND flash. If we can have a vertical electrode like this, then we can make the RRAM materials deposit at the sidewall of this pillar. So then you can have the similarly like a 3D vertical NAND. You can have this 3D vertical RRAM, and then you can just use one lithography to develop this one pillar, and then you can save the cost of the mask. So this is another approach. And here are some examples from the companies. And you basically have this vertical electrode and then deposit the oxide using ALD, atomic layer deposition, to cover the sidewall. And then you can have the electrode to surround the pillar. So it's like a gate-around structure. So you have the pillar, and then you have the sidewall of the pillar covered with the oxide, and then you can have the another electrode surrounding the pillar like this. So you have one electrode, another electrode. So in between you will have the oxide. So you make it an RRAM structure like that. So this is some of the demonstrations. And this is a structure I proposed in my PhD thesis quite a few years ago. So this is a way to make the 3D cross-corner array with this kind of approach. We have the pillar electrode and the plane electrode, and then the sidewall is the oxide. So we can make this like 3D array very similarly as the 3D vertical channel NAND. And there are some other structures proposed by, I think, IMEC. So similar idea, we have the vertical electrode. So the cell is surrounding the vertical pillar. But this doesn't fly, I mean, after so many years. So the key challenge is in the cross-corner array. You know, you need what? Any idea? In this kind of structure? What is challenging there? Can you tell? Cross-corner array, you need what? Selector, right? So that's the key challenge to make this structure. You have to integrate the selector in this kind of structure as well, which is very challenging. Okay, so this is a quick summary, and the near-term application is to serve as embedded non-volatile memory with the 1T1R array, and the long-term application, if we can do the 3D cross-corner array with the possible selector built in, then it may serve the standalone storage class memory. And but still, this kind of device need to improve the uniformity, reliability, and reduce the variability. And then the current, reset current, needs to be scaled down and improve reliability. And this IV nonlinearity is needed for the selector. If you don't use selector, then your memory IV needs to be nonlinear by itself. So it's like built-in selector. So it's very important to demonstrate all good characteristics within the same material system and at array level, because many papers just show some good attributes not all of them in one device. So it's very important to achieve all the good characteristics in one device.
So for the cross-point architecture for RRAM, so these are all single-level cells? Are you able to-
So in principle, you can do multi-level cell, yeah. But the sense margin may be quite low if you consider the selector, because selector essentially suppress the current,
Yeah.
right? So the on operation may not be that large. Depends.
And
But
how
in
would
principle,
you like implement multi-level cell with the transistor? It's just a filament formation, right? How do you make it multi-level?
yeah. In principle, the resistor can be in multi-level, right? By tuning the resistance. So your transistor, when you read it, you are going to fully turn on the transistor. So transistor is fully turned on. That means the channel resistance is very small. So it's negligible compared to the RRAM resistance. So you are reading RRAM resistance. You can read different levels. That's fine. This is for selected cell. For unselected cell, your transistor is completely off, right? The gate is off. Then you don't have any sneak path there. Yeah, so it's okay. Alright, so this is for the RRAM. And then we will continue our discussion. Can you make a